Can you hear me?
Yes, we can.
Excellent. So if you work on the tutorial repository, you can open the Fink one. It will open a notebook in Collab. Okay, so Galactic Science. So what's behind this notebook? Well, there will be two aspects, one on variable stars from our own galaxy, and the other one on microlensing. Actually, we have a module to try to detect microlensing events. So I will split, let's say, the tutorials in two parts. And I will first work with the variable stars. So, well, there are a few things to set up your environment if you need to run it. So each night, we basically cross-match the ZTF public stream live with the Simbad database. So we do that on live using the cross-match service that they provide at Strasbourg. And we end up with roughly 30% of the alert that survive the quality cut with a counterpart in Simbad. So it's not bad, 1/3. The most present types basically are variable stars like RLR type, eclipsing binary, long period variable stars, or Mira type. So we just label alerts. So it's a positional cross-match. So we have a radius of 1 arcsecond, I think. We look, if we have several objects, we just take the closest one. So there might be maybe false association, but usually it's not bad. So let's walk into these different classes. So how you would do that in Fink? So if you are using the REST API, so here is the URL. So you will use the endpoint latest, for example, and you will query, let's say, the 100 latest RLR. And so you can do the same from the web application. So what you would do is you would end up here. You would say, well, I want to search by class, for example. You have a drop-down menu here, and you have like millions of different classes. And everything that starts with Simbad is something that has a counterpart in Simbad. And you can click on whatever you want, and you will see all the alerts that correspond to that one. So for example, here, so we look for RLR, the 100 latest one that were found in the stream. So it will return a list of objects with some properties. Of course, then you can query for a specific object. You can say, okay, this one is the RLR. So Fink, please give me all the data associated with this object. And what you can do is just plot the data. Of course, it's messy. So what you have here is the lower triangle are just upper limits. You have other triangles that are alerts that we receive but didn't pass the quality cuts, and you have the circle that are valid alerts. So of course, you know it's RLR. So what you would like to do is to fold the lie curve and extract some parameters like the period, as exactly was shown by LRC and Antares before. So there is nothing new under the sun here. I will show. You can do that actually from the web application, from the science portal of Fink. So remember, we have all those different views for a given alert. So you can walk to the variable stars one. And here you have a button, you click on fit data, and it will try to fit the data and give you, extract the period for a given object, for example. In this notebook, basically what we'll do is just redo what's under the hood of the application. So the first thing we need to do is go from difference magnitude to DC magnitude, apparent magnitude. Well, Eric Bell mentioned that on the Slack channel, and hopefully we do it. So you have it's just a transformation of units, taking into account different things. And what we use this very nice package actually called Gatsby. It's not me who wrote that, but we use in Fink. We use this package in Fink to do everything related to variable stars. So what it does, it will take the, oops, where am I? It will take the light curve. It will take a model. So here we use a Lambda-Scargel multiband model, for example. You can set up different parameters. You can ask to fit the period. There are many things inside. You do your cooking, and in the end, you end up with that kind of thing. So it's a folded light curve. So the phase and here the apparent magnitude for different band, G and R. And you have an estimate of the period. So in that case, it gives something like 0.5, 0.51. And actually you can check, so either from from that link, but it's also linked in the science portal. You can search in Assassin websites. And well, trust me, it's something like 0.5 as well. So we are not far from that thing. Well, so that's the basic thing you can do. Of course, there are many things. Then you can study population. I won't show here things like that, but exactly like Lorena presented before, you can do some statistics, grab 1,000 of objects, and 30% of valid alerts are tagged in Sinbad. So it's a lot of alerts, like millions. So there are many things to be done. The second thing I would like to discuss is gravitational microlensing. So of course, this is not only galactic science, but it happens more frequently in the galaxy for us because the density of stars is bigger. So it's something that will usually happen well around our galaxy, at least in the stream. So for that, each night we try to characterize, well, we try to find for microlensing event, and we use software called lens identification algorithm called LIA, which has been described in this paper called in SETI 2019. So we have basically implemented that in Fink. Well, behind what it is just a random forest algorithm. So you will extract many different features from the light curve. You will have a model train, and we will try to just well, disentangle between different classes, including variable stars, I think cataclysmic variable, microlensing, and something which is constant, so no variation at all. So one of them is microlensing, and we are looking for those ones. Of course, we are working on alerts with limited photometry size. So we have up to 30 days with ZTF. Hopefully we'll have 1 year with LSST, so that would be better. So keep in mind for ZTF, we are doing that live with alerts. So doing microlensing with up to 30 days is very challenging, very, very challenging. Okay, so we have this module, we process alerts, and all the alerts that satisfy various criteria, including the score of this module, are tagged as microlensing candidates. So you can query them afterwards. So here you would use in the REST API the endpoint latest, and you would, for example, ask for all the latest microlensing candidates. So I set up n of thousands, so 1,000 alerts. This is a maximum. We don't have 1,000. We have actually 428 for about 2 years. In 2 years. So you can quickly look at them if they were previously found in Sinbad, for example. You can see that most of them are unknown objects in Sinbad, and 3 are categorized as fail. It's just like Sinbad was not working at that moment, so just ignore that. So okay, they are not variable stars, known variable stars at least, which is good. It's usually a contaminant for microlensing, especially with such a short time scale, 30 days. You can have a look at the spatial distribution of all the different candidates. So this is a plot in galactic coordinates. In red is basically arbitrary galactic cuts at latitude 20 degrees plus or minus. So you can see you have a few candidates extragalactic, well, considered extragalactic, and most of them were around the galactic.
2 minutes.
Okay, thanks. Well, let's have a look at one candidate. So I took just one. So you can have a look. You use the endpoint objects, so you will retrieve all the data. You can plot the light curve. So this is something like that. And the shaded area showed the data that was favored as microlensing. So of course, the full light curve contained more than one alert. So you have many alerts aggregated. But what matters here is the data that is contained in this box. And here the classifiers say, oh, that's maybe a microlensing event. Okay, great. We're very excited finding something interesting. From the web application, from the science portal, you can walk to the microlensing view, and you can fit the data. So we implement. We are running PyLima, which is a library written by Etienne Bachelet for fitting for microlensing events. So we will take the light curve and extract different parameters, including T nodes, the Einstein time, U0, for example, and we will try to give some quality assessment. So the reduced chi-square divided by the number of degree of freedom. Well, here, just for demonstration purpose, we do the same. So the first thing is we go from difference magnitude to DC magnitude as before. we do all the PyLima magic, and we end up with something like that, exactly as in the portal. So we have the fitted parameters. Well, the reduced chi-square is not too bad, but obviously we don't have the rising parts nor the baseline, so it's very difficult to make any educated guess about the fact that it's microlending or not. So what we can do is request from the ZTF directly data release all the data, not just the alert data, but all the data that is present in the data release. So for that, we use the REST API of ZTF, which is very simple to use. Thank you very much for that. We do that and we overplot. And this is, so here is the alert data that we are considering. And here is all the data that is sitting in ZTF data release. Clearly, it's not a microlending event. So this is unfortunately our life, since now all the candidates are not microlending. This is partially due to the fact that we are using limited photometry. So things that we are doing is first aggregating the data in real time. This is challenging because the database is huge of alerts, it's several terabytes. So you have to make sure that you don't introduce too much delay. For LSST, that would be easier because history will be up to 1 year of data. So that will help us to characterize the baseline, the stability of the flux pre-event, etc., etc. So, well, I would say this is now we are training ourselves for LSST. And I'm stopping here if you have any question.
I see that there was one question in Slack, but it looks like he's already answered it. I applaud the efficiency.
It's a team effort.
Yep. So I don't see any other questions. If you do have any other questions, obviously drop those in the Slack as well, and the speakers can get back to them. And I think that should be it for this session.
Thank you.